Hey guys, Mr. Gron with 8.5 Challenge. We're going to talk a little bit about extraneous solutions in this one. Okay, so looking at this, I took this right out of the pre-calc textbook. So this is a good one if you're to look at if you're going to try to take pre-calc next year. Um, so looking at this, we know that we want to start by figuring out what the least common denominator is. And in order to do that, we're probably going to want to do some factoring. So if I start factoring this out, the 2 over x plus 2, well, that one doesn't factor. I'm going to skip the middle one for now, and I'm going to move over to here. We've got an x squared plus 4. No sum of squares, right? That doesn't factor, at least not without complex numbers. And the bottom factor is our difference of squares, which is x minus 2x plus 2. Okay, good. So I've got a matching one. But now this one in the middle. Now, if you've seen some of the previous videos I've done, I had one very similar to this. And the trick here is we're going to rearrange the order of these two. And that's really a common thing in like tougher high school math type classes. All right, so now we've got x plus 2 here, this negative x plus 2. Let's focus on that. This negative x presents a problem, but I can solve that problem if I factor that negative out. That's the trick for almost all of the ones that look like this, where it's a negative for the leading coefficient. Factor that negative out. And so let me give myself a little more space here. If I take out that negative and put this in parentheses, that's going to change the x from a minus x to a positive x, and the 2 from a positive 2 to a minus 2. And so now I've got some matching factors, right? I've got a plus 2 here, a minus 2 here, and then a minus 2 and a plus 2 over here. Now I still have this negative here that I can monkey around with a little bit. Now it turns out that it doesn't really matter where that negative is on the fraction, right? I can move it right in front of the fraction bar, and that might make it easier to see the next step. If I subtract a negative, well, it's the same as a plus. And now this problem just got a lot simpler. Okay, so our next step, let's go ahead and identify that x cannot equal positive or negative 2, right? Because that would cause a denominator to be 0 for, a couple of the denominators. It doesn't matter as long as one of them is 0. The whole thing is undefined. All right, and so now let's make the denominators disappear. So we're going to multiply everything by x minus 2, x plus 2, all three terms. Now remember, that is allowed as long as we do the same thing to all of the terms. Everything stays balanced. Let's see if I can write this backwards. That wasn't too bad. Okay, so now we can cancel some stuff out, right? The x plus 2 cancels here, the x minus 2 cancels here, and then everything cancels here. And now I don't have those pesky denominators to worry about. So we'll rewrite everything. Distribute the 2 into the x minus 2, and we get 2x minus 4. Distribute the x into the x plus 2, and we get x squared plus 2x. And then on the other side, it's just x squared plus 4. All right, let's combine some like terms and start cleaning this up. On the left-hand side, it would be x squared. There's 2 positive 2x's makes 4x, and a minus 4 equals x squared plus 4. Now this one's kind of curious because I've got a positive x squared on both sides. Now when we're working with quadratics, we usually try to move everything to one side, but I'm going to take that in 2 steps here. Because if I subtract x squared from both sides, look at what happens. The x squareds go away, and now it's a linear. So let's rewrite this over here. 4x minus 4 equals positive 4. So now just add 4 to both sides. We get 4x equals 8. And if we divide both sides by 4, we get that x equals 2, except x can't equal 2. So we've got an extraneous solution. So this one has no real solutions. our solution that we found is extraneous. And so the next part of this video is to talk about why extraneous solutions are a thing. Um, it's really common in math classes to just sort of gloss over this and just sort of treat extraneous solutions like they're just this weird, random, magical thing that happens for no reason. But I'm here to tell you that in your math class, in your high school math class, everything has a reason, everything has a logic and an order behind that, and things are very predictable. And that's the same with extraneous solutions. We just don't really talk about them that much. We just kind of like say, just double check that your answer is right, and if it's not, it's extraneous. But there is a little more to it than that. So this is one from the actual lesson, not a particularly tough one. But before I get into that one, I'm going to do an even simpler equation, and I'm going to solve it in a very unconventional way to show how you could potentially come up with any extraneous solution that you want and be correct. So if we look at the equation x equals 2, right? That's about as simple as you can get because, well, 2 equals 2. So the solution is 2. In fact, that one's so simple that if I put that out there to you guys, you might get confused and not know what to do. All right, so that's one way to solve it, probably the most logical way. Another way to solve this would be to multiply both sides by x plus 2. Now, this is very similar to how we solved the previous problem and very similar to how we would solve this problem, except that these don't have denominators, or their denominators are 1. So we just normally wouldn't do this because it doesn't make the problem easier. However, it's still allowed. I'm still multiplying the same thing on both sides of an equation, so there's nothing mathematically illegal about this. But let me show you what happens here. Okay, so if we distribute the x in on the left side, we get x squared plus 2x. And if we distribute the 2 in on the other side, we get 2x plus 4. Okay, so now I've created artificially this quadratic, and I'm going to start moving things to the other side then. So now the 2x's will cancel each other out, the plus and the minus, and what I'm left with is x squared minus 4 equals 0. Now this, we could solve it algebraically, or we could just factor real quick, plus 2x minus 2, and we get that x is equal to positive 2 and negative 2. But now, if I go back to my original equation, right, only one of those solutions solves it. Now, everything I did was mathematically valid there, but only one solution actually works, right? Negative 2, if we plug that in, it doesn't work. So this is, negative 2 is an extraneous solution. And that's just as correct as just saying that x equals positive 2, as long as I identify that this is indeed an extraneous solution. And just to go a little bit further with this, let me erase that. If I plug in that negative 2 into the equation that I created by multiplying both sides by x plus 2, it kind of makes sense that this just multiplying both sides by x plus 2 would yield a solution of negative 2, because if I change that x to a negative 2 and this x to a negative 2, well, now these factors, 2 minus 2 is 0, negative 2 plus 2 is 0. It's 0 times x equals 2 times 0. So you could do any number, x plus any number or x minus any number on both sides to come up with whatever extraneous solution you wanted. Okay, so let's take a look at another way of looking at extraneous solutions, how they can be predictable in something that's not quite as ridiculous as the last one. Looking at this problem, the way that we solved it in class was to identify, okay, this has the factored form is 2 times x minus 2, so I'm going to multiply both top and bottom by 2 times x minus 2, right? Now, there's another way that we could do this. We could instead just multiply it by x minus 2 on both sides. And what will happen there is we won't cancel out the complete denominator on the other side, but we will cancel out all of the variables. And so what we are left with is 5x over 2 equals 3x minus 1, right? And another way to write 5x minus 2 is 5 over 2 is 2.5x. Well, now we've got a fairly simple linear equation to solve. All right, let's look at the desmos of this. I'm going to get rid of some of this stuff. So just looking at these two, the red and the blue equations, those are the two equations that were given in the problem. And they're here in red and blue. And so what we're really looking for when we say that two equations are equal to each other is where do their graphs intersect? That's where they both have the same input and output. And these ones are really, really close, but the red and the blue don't actually ever cross. I double checked, and they get really super close to each other, but they don't actually ever cross. Now, when we started doing the math, when we got rid of the denominators, we changed this equation. We changed it from a rational that had both x's in the top and bottom of the fraction to a linear that only had x's like to the first power. There was no fraction anymore that involved the x. And so what we did is, in order to solve these two really actually complicated functions, we used some algebraic trickery to make them into two simple functions, two linear functions. Well, the problem with the solution to this is that where the green and purple line cross, which represents the two equations after we got rid of their denominators, is that their solution is right here where x equals 2. And the problem there, of course, is that x can't equal 2 in this, because that would be undefined, right? It's right on their vertical asymptotes. And so what's interesting about this is we can use this to predict other extraneous solutions or other equations that would have the same extraneous solution. It turns out that if we made the numerator of this function, 3x minus 1, if we made that any linear equation, instead of 3x minus 1, we put anything that had that intersected at the same point here, that would also have the same solution, the same extraneous solution. So like negative x plus 7, that crosses through that same point. Y equals 5, that crosses through that same point. Those would be two other equations that would yield the same extraneous solution. So we could say that, get rid of this, if we set this equal to negative x plus 7 over x minus 2, that's also going to give us a solution, an extraneous solution at positive 2. And if we set it equal to 5 over x minus 2, that's also going to give us that same extraneous solution.